Hello, everyone. Good afternoon, and welcome to this talk of the Ming-Hsieh Institute Seminar Series on Integrated Systems in collaboration with the IEEE-SSCS Joint Student Chapter at the University of Southern California. Today, we are pleased and honored to have this talk presented by Professor Sohmyung entitled Near-Field Data Transmission for Biomedical Implants. Professor Sohmyung received the BS, summa cum laude, and the MS degrees in electrical engineering from the Korea Advanced Institute of Science and Technology in 2004 and 2006, respectively. From 2006 to 2010, he worked at Samsung Electronics as a mixed signal circuit designer for commercial multimedia devices. After this extended career in industry, he returned to academia as a Fulbright scholar and obtained the MS and PhD degrees in bioengineering with the Ingelson Best PhD Thesis Award for Biomedical Engineering from the Department of Bioengineering at UCSD in 2015 and 2016, respectively. Since 2016, he has been an assistant professor at New York University, Abu Dhabi, and a global network assistant professor at New York University, USA. He currently serves as an associate editor of IEEE Transactions on Biomedical Circuits and Systems and Frontiers in Electronics, and served as an associate editor of Smart Health, Elsevier, from 2016 to 2021. He is a member of the Analog Signal Processing Technical Committee and the Biomedical and Life Science Circuits and Systems Technical Committee BioCast, TC, of the IEEE Circuits and Systems Society. He is also a member of the IMMD subcommittee of the International Technical Program Committee of the International Solid-State Circuits Conference. Professor Ha, we would like to welcome you again, and the floor is yours.
Thank you. Thank you, Michelle, for kind introduction, and also, thank you, Professor Studies, for hosting me here. And I visited this class this year, and then I would like to stay in the stay in California further. So I came down to the LA, and then I'm honored to visit the USC. Okay, I'm from Abu Dhabi in the UAE, so I wanted to start with my presentation with where I'm from. Sorry, probably I can take this out. I don't know. Anyway, NIU, New York University, is one. Yeah.
Oh. I think, yeah, on the Zoom, it's perfect. It looks perfect.
No, but we need to see it.
Yeah.
Option reaction. Hide. Oh, okay, good. Okay. So I'm from NIU Abu Dhabi, and then but NIU itself has about 15 global campuses in the world, all over the world. Now, among them, 3 campuses offers degrees: New York and Abu Dhabi and Shanghai. Some people may have heard of Abu Dhabi first, but Abu Dhabi is placed in that area, just in the middle of Middle East, just beside Saudi Arabia, Oman, and then Iran. And UAE, United Arab Emirates, is actually a congregation of 7 kingdoms or 7 states, so that it is called United Arab Emirates. Emirates is equivalent to the states in English. And Abu Dhabi is the biggest, and also it is the capital city, and then just 1 hour from Dubai, which is the most popular in these days. NIU Abu Dhabi is located in the outskirts of the Abu Dhabi, and then it is target for world-class research and with liberal arts and science college. It is not a big college. It has only 2,000 undergraduate students and then some PhD students, but we aim for high quality research and high quality and world-class research and high quality education. Without further ado, let's talk about the near field data transmission for biomedical implants. Probably you have heard of this term, but where can we find this in our usual life? Actually, in my case, every day. When I entered my room, I used my key card, and then also even this morning, I use my credit card. We content this card transaction for my breakfast. So here, near field power and data communication is embedded there. So if you look into the credit card, then it looks fancy outside, but inside is quite simple. It has some chips there and then some contact paths, which is for the contact to the external device. And except that there's 2 chips and then 2 cores, that's it. And then they are quite similar, one for the power and data telemetry, and then the other also for the power and data telemetry, but for the different frequency. So whenever please note that inside of the card, there's no battery, so that it can be very compact, or it can be very thin there. Just the frequency and then protocol are different. So one for the 13.56 megahertz, and another for the
Like a multi-standard phone.
That's right. Yep.
So different readers support different frequency flight protocols. So.
That's right. And then when we place the card just above the card reader, the coil of the card and also the coil of the reader is aligned with a very short distance. And then the card reader send the power to the card, and then they do the data transfer back and forth. So in that case, typically we use only one single carrier frequency for the power and also for the two-way communications. Please note that, again, the card itself does not include any batteries, so they can be very compact. And also, it is great for the on-demand operation. I mean, it's great for security, so that card does not work randomly, so it operates whenever we place just near the card reader, and it is powered up so that you can operate that. So it is great for security there. So RFID or this near field communication or power transfer and backscattering or backward communication has been used for many places with the RFID tags. It has been used for lots of applications, especially for identification and access control, and also product tracking and management. But these days, it has been used in the implantable medical devices, which is our today's topic. For example, this technique has been used for brain-machine interface. The brain-machine interface, which requires a lot of power to operate inside the brain. Also, lots of communication data rate is required to send out the massive data to the external side. Also, there's another example for the retina prosthesis, which is a retinal implants to restore the vision by stimulating the retina. And also cochlear implant, which is the device to restore the hearing to stimulate the cochlear from the stimulation from the sound processor outside of the body. Also, there are other medical devices that requires wireless power and data transfer. When you say the power, then probably you may think about the battery first. Yes, batteries are great and then very traditional, but there's some issues. These are some examples of the batteries or ultra capacitors. The issue is the energy density. So because of the limited energy density, it should be either a very large size, or it has very limited time, or it needs frequent charging. Please note that we need the medical device that can stay inside of the body for multiple years, not just few weeks. So it means that it requires lots of power energy, but the energy density of the battery is not enough. It is great for the medical devices with a small power consumption, like a pacemaker. It can stay there for 10 years. But for the brain implant or retinal prosthesis, that requires a lot of power. The battery is not an option. Then next option could be energy harvesting. Then it is quite ideal. You can obtain energy from the environment, but still it has the issue of small output power. And then that output power is proportional to the volume itself. So the bigger the size, the bigger the power. So it is great for the big implants, but also there's some limitation though. It is quite location specific. It is kinetic energy based, motion based energy harvesting can be done in the limbs, but there's not many things that we can do for the implantable devices in the limbs. We need lots of power, probably in the near head area or chest area. So there's not much of an option for the energy harvesting. So there's some discrepancy between the requirement of the location and also requirement for the harvesting. The next one could be transfer. Yes, we can transfer power. There are several ways. The ultrasonic, we can use a light. Also, you can use an RF harvesting. So inductive transfer. So today, I'm going to focus on the inductive powering. There are pros and cons, but I will focus on the inductive powering today. And then before talking about the inductive data transfer, probably we need to know some fundamentals of inductive coupling and then inductive powering. So as far as I know, all of you are in the circuits area, and then RF, and then some may be in, some may have expertise in ADCs and PLO might be. So it should be very easy questions to the RF community, other people. Near field. Then when they say near field, it is related to the distance between the two antennas. So if the distance between the two antennas is within the one wavelength, we call it a near field. And then if it is above the few wavelengths, then it's a far field, which is the case for the BLE and then cell phone. Okay. What in our case, in the biomedical side, the wavelengths of interest is about here. So when you use a 13.56 megahertz wavelength is 22 meter, and sometimes we use 100 megahertz or similar range, then in that case, 3 meter. Then what about the distance in our case? This is the cross-section of the cochlear implant. Here, sorry, can I find the cursor? Screen power options, sorry. No, that's fine. So here, here's an implantable coil, and then just across the skin, there is a transmitter coil. So these two coils are placed just across the skin. So it is just a few millimeters. Then what about the brain implant? There are several configurations of the brain implant, but in this case, we assume the brain implant's coil is placed just above our cortex, just under the skull, and then the power transmitter is placed above the skull there. It seems far, but it's just 1 centimeter. So it means that the wavelength is 10 meter. Our case is just like this, like 1 centimeter or a little bit larger than that. So it is quite deep near field. So it means that the powering and then everything is not based on the radiation. Also, all the phases across the whole system is the same. So it means that we don't need to worry about other stuff, but we can assume it is a magnetostatic conditions. So we can analyze whole circuit using the inductive coupling, which is learned in the undergraduate course. Okay, we have two coils, L1 and L2. Inductance can be calculated with the geometry. Self-inductance calculated like that. And then mutual inductance is, we all know about the mutual inductance, but mutual inductance can be normalized with the L1 and L2. Then we can get the coupling coefficient, which is a K. And then this is the matrix between the 0 and 1. And then it says that how tightly the two coils are coupled. The 0 means no coupling, 1 means perfect coupling. And then for the implantable devices, 0.1 or 0.2 is just rough number or typical number for the coupling. When it is a tightly coupled, it can go up to the 0.5. If it's lowly coupled, it can go below the 0.1. Then quality factor, we all know about it. Quality factor is omega L over R, which is proportional to the frequency. So it is the ratio between how much energy is stored versus how much energy is dissipated by the coil. Because of the conductance resistance of the coil, so we can model the coil with a perfect inductance and then resistance in series. Okay, with that, we can transfer the power. Okay, here we drive one coil with a sinusoidal waveform, then the coil will generate the magnetic field, and then that magnetic field will be coupled to the other coil. And then because the magnetic field is a sinusoidal wave, sinusoidal means a time varying, then time varying current will be generated, and then you can direct the current to the load so that then we can transfer the power from one side to the other. Then in terms of circuit, we can draw like that. And then we can add the capacitor, so we can utilize the resonance there. So we coupled, we can match L1 with another capacitor, L2 with another capacitor, so that we can maximize the power transfer. Here, this is called the primary side, this goes the secondary side. All right, then here I want to show you how much power we can deliver by the inductive, the AC resonance there. Here, this is a non-resonant inductive link case, and this is a resonant link case. I added just C2 only, so I want to show you how much energy we can get further. This is a voltage across the load, and then it has this factor so that this one and this one is canceled later, so that the denominator gets smaller at specific frequency. But if you do the simulations, then it seems like this, so that this is a non-resonant case, this is a resonant case, so that at the resonant frequency, we can gain like a 10 times-ish bigger power delivered to the load. And then if you utilize the resonance at the primary side, then we can get the further. Okay, now I want to show you how to analyze the circuit a little bit easily. Here, with the given, this is a basic circuit for the inductive powering. Yes, we can solve by hand, but if you use this technique, then this small technique, then you can simplify further. The R2 here can be converted into the parallel capacitor when the Q2 of here in the AC tank is large, especially in that case, IP2 is similar to the Q2 square of R2, so that all the circuit becomes a single node pair circuit. In that case, this one can be combined. And then this whole secondary side can be reflected to the primary side with the K value there. It seems complicated, but we are in the resonant frequency. We are in the single frequency. So we are going to use a single frequency for the power transfer first. So in that case, L1 and C1 can be canceled, and then L2 and C2 be canceled. Then in that case, the whole circuit becomes like this. It's quite simple. So here we have a R1. Yes, this RL2 is a parallel combination of IP2, which is a converted series parallel converted resistor, and then we have RL. Then power transfer efficiency, which is the ratio how much power can be delivered to the load, can be calculated very easily. So it is simply the voltage division between the R1 and RL2 and the current division between these two resistors. Yes, these two. And then if you rewrite with the known values, then it can be rewritten like this one, but still they are the same. Basically, the voltage division and then current division. And please note that this one L, the load, here's RL, here in the numerator and then denominator, then we want to find the optimal point, so that we can achieve the maximum power transfer efficiency. In that case, if you do the differentiation, then we can find this value that, okay, this value is the optimal load condition for the maximum PTE. So here's an example. So this is a PTE and this is a load conditions. So we might think that we can have the certain load condition to maximize the PTE, but the case is opposite. In most cases, RL is a predefined. It means that for most applications, RL is given 100 microwatt or 10 microwatt or something like that. So it is quite difficult to change RL. So it means that with the given RL, we need to optimize other circuit parameters like L2, C2, and other stuff. In many cases, Q2 should be maximized, so we don't need to worry about the Q2. So we need to achieve the maximum Q2 as possible. And the C2 is determined by the L2, so we can read to the L2 design. In that case, there could be not many options to implement the magnetic coil. Probably we can use wire-wound coil in many cases, but sometimes for the small implants, it's not the case because of the space issue, because of the volume. Then also, so that still many implants like to use this kind of coil too, like a printed spiral coil. It requires a smaller volume, although its achievable inductance is smaller than the solenoid wire-wound coil, and also it can be fabricated on the flexible substrate or even on the semiconductor chips. So because when it fabricated on the semiconductor chips or flexible substrates, we can have very lithographically defined resolution, so that it is great for the batch or mass productions. In that case, here's an example. Here, this is an example chip that we developed some years ago. Here we used the top metal for the wireless power and data transfer, and the inside it includes all the circuitry that requires all the recording and the AD conversion and then everything. In that case, it is placed on the brain surface here, and then we place the TX outside of the skull. Then this coil, this one has, as you can see, we use a spiral coil there. Then this one has the L and the R in series in terms of a model, and then we can say the quality factor is omega L and R. Yes, for sure. But and also please note that this is a proportional to the frequency, but in reality it is not. We all know that it is not. As we increase the frequency, initially, yes, it is proportional to the frequency. This is a quality factor, and this is a frequency. And this is a 1 turn, 2 turn, and a multiple number of turns. But after a certain frequency, it gets degraded, and even gets degraded even further. Then there are other stuff to consider. So this is not a perfect model. We need other circuit components. Still, it is not a perfect model yet, but still you can capture the other effects. So let's talk about some circuit model first. L, this is straightforward. We can accurately calculate or accurately simulate the L. But what about other circuit components? RS, it is the resistance. Yes, it is. It is the total resistance of the conductor. Yes, it is, but at low frequency or at DC. We need to consider the two effects. One, skin effect. So as we increase the frequency, and then the flow, the current flows near the surface only, so that the effective area gets decreased, so that resistance gets increased. And also there is a current crowding effect. So please note that this inductor is placed under huge magnetic field for the power transfer, so that eddy current is created on the surface of the coil itself, so that it hinders the current flow. So that gets increased the resistance of the inductor. Also, this one, there is also capacity components in the inductor. Yes, there's a coupling capacitance. We need to consider that. And then also these two model the realistic application of the implants. Please note that the implant is inside of the body. So it means that here there will be a coupling from the implant to the external side, and then in the external side we'll be placing the some fluid, human fluid, which has a lower or some conductance there. And then this one, depending on the distance, depending on the size, but it's about 100 ohm to 1 kilo ohm, so that there is these kind of effect there. In consideration all of this, then quality factor gets degraded as we increase the frequency. And then with that, we can simulate that PTE at a certain node, and then with the multiple turns, then all with the HFSS, then we can determine the optimal frequency and an optimal number of turns. Okay, now let's move on to the communication side. Any questions so far? Yes.
This is the effect of misalignments for the teaching.
Yes, that's great questions. Yes, it impacts the wireless power transfer. So whenever there is a misalignment or an angle mismatch, then K value will be changed. Then the total power that is transferred will be changed. Then we need to adapt to it. Yes.
Thank you. Maybe to add on to that, like how sensitive are some of these realistic implants to a little bit of misalignment? For example, like if you have like a brain implant on one side under the skull, potentially that maybe might shift a little bit or something like that. So how much variation is tolerable? Like if you have like maybe 10% variation, how much loss in power would that correspond to for a typical system?
Good question. So whenever we use the implant, then system will be something like that. So it means that TX antenna is much larger than, bigger than the implant. So that within this range, it is okay. If it's outside of that range, is too much of information. So within this range, as a rule of thumb, 10% or 20% will be degraded as a rule of thumb. And also bigger issue is alignment there. So I mean angle alignment. So if its angle is quite different, then depending on the angle, it gets worse. So the angle is more important. So in the real applications like cochlear implant, it typically has a magnetic there, so that it can ensure the tight coupling. Yeah. Yeah. Mm-hmm. Okay, communication. So please note that it is not a standard communication protocol. It is quite special case. We have two coil, and we are sending power from primary to the secondary side. And on top of that, we want to transfer the data, maybe forward data and backward data. So when you say the forward, it means the primary to the secondary, and backward means implantable to the external side. Or sometimes it is called downlink and uplink. Then it's a quite confusing word, but when I say downlink, then I always think that there is a external side on top of our head, and then we are transferring the data from the external device to the brain implant down in the downward. And then whenever it's uplink, then a brain implant to the outside. Okay, with that, probably we may consider the other RF communication protocols or circuits to transmit the data back and forth. They are great. Yes, they can achieve high data rate and they are well established. But issue is a high power consumption, especially on the implantable side. Depending on which implant we are talking about, but some implants have very limited power, like less than 10 microwatt or sometimes, or even less. So I didn't consider this one, but still there's a very good room to use other RF communication for the brain implants and other implantable devices for sure. Also, we can consider having another inductive link for the data transfer from forward and backward. In the case, because of the two coils or even three, they need a complex antenna structure to avoid the crosstalk. And also, whenever we send out the data from, especially from here to here, we need to drive the inductor. That requires high power consumption. So, but when it's shared inductive link for data transfer, in that case, it is quite simple and we can implement it into low power consumption. I will show you how, but the problem is the data rate. We cannot achieve the high data rate in the case. But here, I want to show you some techniques that tackle the data rate issues for the single link cases. Okay, first, let's talk about the forward inductive data link, data transfer. They are massively used for retinal prosthesis and cochlear implants because they have as many as electrodes or stimulation electrodes for the retina and the cochlear. So that means that we need to send out the stimulation information as much as possible. So they need mega BPS or even higher downlink data rate with a very high power consumptions, like tens of milliwatt. But the forward communications is required for almost all the medical devices because at least we want to set up the configuration of the medical devices or make some changes there. So low data rate downlink is required for all the medical devices, but especially high data rate communication, forward communication required for the prosthetic devices. Okay, when we send out the data, we might think about these kind of modulation scheme, like a frequency, phase, or amplitude shift keying. But please note that we have resonant SC tank on both sides. So it's a little bit tricky or difficult or long time to do the frequency shift or phase shift. Even with the amplitude shift, it's difficult too. It takes a long time to settle, but still, it's a little bit better than the frequency and the phase shift keying. So in many cases, for the forward communication, amplitude shift keying is used, but the issue is a data rate there. But when you say amplitude shift keying, then in that case, we send out the power in sinusoidal waveform with each amplitude being modulated then in that case, it is a transfer to the secondary side. And then here on the secondary side is I model as a one register, but it's not the register, load register, it is a circuit. So it is modeled with the two paths. One is the rectification path so that we can rectify the sinusoidal to extract the VDD. And then also in another path, we can have amplitude demodulation circuit so that we can extract the data. It is simple, quite simple, but issue is the data rate. Here's an example. So this is the implant that I developed, and then I showed you before that this is a millimeter size implants that have on-chip foil. Then here we send out the power, and then yes, with that we can extract the power and the data for sure. But if you look at closely, and then when it's a ASK, where this method have a limitation in the data rate, but one of the limitation happens here. So we change the amplitude, and then whenever change the amplitude from one amplitude to the other, it requires a long period of time to settle. So whenever switch one amplitude to the other, we need to wait this much of time to be ready to send another bit. So that limits the data rate. So data rate here is limited by Q1 here. And either we need to sacrifice a Q1 to achieve high data rate, or we need to stick to the low data rate there. Then how can I address this issue to achieve high data rate and also maintain the high power transfer? We can do it using a one switch here. Yeah, we have a switch on the ground side in series here. We're going to turn on and then turn off to do the on-off keying, changing the zero amplitude and the maximum amplitude. But we turn off the switch at a very specific timing. Turn off the switch when the capacitor voltage is at its maximum, and then the current is 0. So it means that all the energy of the AC tank is stored in the capacitor. So if you turn off the switch at that moment, then during this turn off period, all the power is stored across the capacitor so that we can kind of store all the energy, and then finish the opening after the integer number of cycles. So it means then right after that, all the energy was stored across that period of time, and then also it is in phase, so we can immediately start the oscillation there. So we can switch one amplitude and then the other very quickly without waiting for the resonant recovery. Then because this opening can be done in a the period, you can control it at a resolution of the period. What we can do is we can do the pulse width modulation, like we do the 2 cycles opening or 3 cycle opening. We can change that. Also, we can change the position there. Then in that case, we can map the 2 bits for the one symbol so that we can transmit the 2 bits for the 5 cycles or 10 cycles or a certain number of cycles, so that we can achieve relatively high data while not sacrificing the power transmission. Still, there's some drawback though, because during the opening, this period, we are sacrificing the power transmission because we are not transmitting power, but still we can achieve very high data rate. Okay, before moving on to the backward, I want to introduce some interesting technique utilizing the resonance using the multiple link. Here, when I say multiple link inductive data and power transfer, because we are allocate another separate inductive link for the data, we can easily achieve high data rate, but still there's some other power consumption, complex antenna structure, and especially crosstalk issues, but there's some interesting technique here. Here, it is called the pulse harmonic modulation. We have a two inductive link there. What we do is we are sending a one pulse there. If you send a one pulse, what happened in the RX side is we have resonance, like this one. Because of this long tail, because of the long resonant tail, we need to wait this period of time to send another bit. But what they do is they send another bit in the same TX, but in the opposite polarity, and then with a certain reduced pulse, then they can cancel out this tail. So with the two pulses, they can initiate this response on the receiver side, then they can send data relatively very quickly, 1101 or something like that. Also, another issue here of the multiple link is a crosstalk. Especially crosstalk from the large power, but in order to avoid the crosstalk, they could use this kind of antenna structure for the orthogonal or other this kind of things. That's fine, but they can avoid the crosstalk between the power and the data communications, but they require a very complex and very large antenna structures. So there's one interesting work that utilized the crosstalk even. So the most severe crosstalk is from the power transmitter to the data receiver, because we are driving the data transmitter, so we don't need to worry about it here. And then also the power signal received on the power coil is larger than crosstalk from the data, so we don't need to worry about here. But the crosstalk from here to here is the most severe part. So what we do, here, what they do is, so in the RX side, this is an interference from the power coil. And then in the TX, they send the two pulses within a one wavelength. Then if you look at closely what happened in the RX side, okay, this is a TX and this is receives a sinusoidal waveform. And then here, the dashed line is the waveform without the pulses, and then the solid line is the pulses waveform with the pulses. So if you look at closely over here, there's some changes of the geocrossing. So that if you detect the geocrossing, then we can demodulate the data. So even with the power signal crosstalk, they can send out the data very quickly, because this happens within one cycle, so that they can transmit the data they can achieve a high data rate.
Both of these interfaces, same frequency? Like that both LCs are resonant at the same frequency?
Yes.
Can't they just shift them?
They can.
To avoid this.
Yes, they can.
Another question that I had was on the first approach, single link. You mentioned being limited by the quality factor on the TX, but you're also limited by the quality factor on the RX, right? Because you're going to have a ring down, and so if you're essentially turning off your TX, like you're stopping the TX and like with the switch essentially, then your RX is still going to have to like decay down before you can set it up. Right?
That's a great point. Yes, it is. Two things. First, even with in the RX, in the TX side, yes, even when the amplitude is changed from one amplitude to the other, the Q factor affects there, so that there will be the resonant recovery happens, so that might limit the data modulation, but still with some amplitude changes, even not reaching to the stable point, we can detect the data, but also quality factor on the secondary side is much smaller than the primary side. That's an fact. Because
It's not as big of a deal because it's not.
yes, and also quality factor coil is a smaller because of the limited space to build the inductor and also the load resistance. So we have load resistance like all the circuits that we consume. So because of this load, the quality factor is degraded. But still, depending on the size, depending on the applications, the quality factor is around 10 to some tens. But still, even with the resonance here in the receiver side, we can detect the data. Yeah. Good question. Okay, here's one summary for the board telemetry. So the ASK, in this case, yes, we can achieve relatively high data rate, but by sacrificing the power telemetry. Suspend carrier modulation, which modulate the data by switching on and off the AC coil with at a very specific timing for the integer number of cycles. Yes, we can achieve relatively high data rate, like a 9 Mbps with the 27 megahertz. But the issue is power index, which is how long we can use the time for the power telemetry. So because we open the TX certain number of periods, certain number of integer cycles, so that in that case, 50% of the time used for the power, 50% used for the data modulation. So still, this is an issue, but still, in terms of energy per bit, it's much larger, much smaller than other multiple link cases. In that case, these one, because they are driving the inductor directly, so they need to use lots of current. But in this case, they are just turning on and off the switch to transmit the data so that they can achieve very high power efficiency there. Okay, let's move on to the backward inductive data transfer, which is more challenging. So it is widely used for the brain implants, because for the brain implants, they requires to transmit massive data from implant to the outside. So if you assume it is just, if you're using just standard RF transmitter, then it means that you need to drive the antenna from the limited power that is transferred outside. Yes, as I said, our main challenge of power and data telemetry for this application comes from the location itself. So implant is placed in quite a limited space on the brain or near the brain. Because of this space limit, the antenna size is quite limited. I mean, antenna for the power transfer and also battery size too. So it means that it requires it will inevitably have very small size, and then the available power is very small, so all the circuits should be low power. But at the same time, we need to transmit lots of data from the brain to the outside. We wanted to record as many electrodes as possible. For example, ECOG, electrocorticography, which records the brain on the surface. It records the brain signal. With 1,000 channels, it requires a 60 megabps. Or when you record the neural spikes, in the case with even 100 channels, it requires a 6 megabps there. Then, I want to show you how to address that issue.
Go back to the slide. What is the power estimate that's going into the brain for those cells? Like, let's say that I have like a sensor outside the brain and I'm sending power. What is the typical power that I'm sending at that power level?
that depends on the configuration and then also size of the brain, size of the implant. What I'm saying is the configuration is we can place the antenna on here, or sometimes we make a kind of hole in the skull so that we can place the implant in place of the skull so that antenna can be placed over here. And then some implants have antenna here, and then there is a hole and then brain implant over here. So depending on that, and also size of the antenna. So
I assumed, like in the beginning, when you talked about the specific frequencies for those biomedical applications, I assumed that the human body will be transparent to the magnetic field of those frequencies. Is that assumption true?
it is true in terms of magnetic field, but it does not mean that the magnetic field is not observed by our body.
Oh, okay.
So in terms of transmissions, yes, it's true, but there's some limitations that we can transfer the power to the body because of the tissue obstruction. So we are worried about the RF
tissue damage, right?
tissue damage, yes.
I see. So, but when you go like to the slide where you have like a typical power transfer, it's different for different parts, and the brain was like showing the maximum of like 100 megawatt or something. Is that typical not to damage the brain tissue like 100 megawatt?
It will, because whatever we transfer to the brain, brain implant will consume that much of a power, then that will generate the heat.
I see.
Yes, that's another factor. So when we transmit the power, that electromagnetic wave is observed out of the body, so that there is a very strict limitation to how much we can transmit the power at certain frequency. But that I had a slide for that, but I skipped it. But as the frequency increase, our tissue, the more our tissue was served. So we would better use a lower frequency in that sense. Then we can transmit more power at a lower frequency. But the issue is when the implant size is smaller, then it's quite tricky to use a lower frequency.
Yeah, and that's a problem. So I know that in terms of the efficiency of rectifiers and stuff, it's better at the lower end of the frequencies. But what I know that if we have that teeny tiny chip that's sitting inside the brain with not a massive coil inside it, that is gonna like limit the efficiency anyways, because the coupling now is gonna be like nothing at all, since you have a very, very small coil and you're not coupling anything.
True.
So the trade of like going to a higher frequency, let's say, for example, you go to 1 gigahertz, for example, would that be not transparent and you get like too much absorption in terms of the human tissues and stuff?
There will be huge absorption by the human tissue, so that not huge, but still there is some room for the power transfer. In that case, let's assume the implanted size is a 3 by 3 millimeter.
Yeah.
And then in that case, we use 140 megahertz. Because we could transfer like up to 100 microwatt using 144 megahertz. And then if the implanted size gets smaller, then we need to use higher frequency because of the antenna size. In the case, because of the smaller size of the antenna, because of the high frequency, the power that we can get gets smaller and smaller. Then it is because of the
more different to achieve the data rates with like very, very small for that you can harvest the chip anyway.
Yeah. So it is a challenge. That's why. But that's why some groups wanted to use some different configurations so that they can place the power coil just under the scalp above the skull, so that they can get a smaller distance, so that they can transmit lots of more data there.
Thank you.
Okay, before moving to the other techniques, then we need to know the conventional technique first, LSK, load shift keying. The load shift keying is just the shift the load from one load to the other. In that case, we typically use a one switch across the load or across the acid tank so that we can make the load to be zero, effectively. Then because the load is changed, and then because of the inductive coupling, that is reflected to the primary so that we can detect the data there. But please note that we are not driving the coil to transmit the data from the secondary to the primary, but by using turning on another switch, then we can transmit the data. If you look into the circuit that we drive before, here we have whole circuit gets like simplified like the 2 resistors or 3, then we are shifting the RL. Because we are shifting the RL, RL2 is shifted. So it means that the current across through the primary side or even the voltage wherever in the primary side gets changed. So by shifting the load on the secondary side, on the implant side, that is reflected to the primary so that we can detect the data. Now this is the backscattering or load shift keying. And then this technique is used in our credit card and also the access card. Okay, here again, there's a trade-off between the power transfer and the data rate. In the case, I would say on the Q2, even though Q2 is small, but we have to maximize the Q2 for high power transfer efficiency, but also for the data transfer, we need to minimize or we need to reduce the Q2. And then typically it's inversely proportional to Q2. It can be explained with the resonant recovery. So by turning on and off the AC tank, the amplitude becomes 0, and the maximum we need to shift the amplitude 0 to maximum. But because of the resonance, it takes time to be ready to send another bit. It takes 5, 10, 12, 40. So because when the Q2 is greater, and then the resonant recovery times gets longer, then the maximum achievable data rate gets smaller. And also, we talk about the energy efficiency, but whenever we short the coil here, we are shorting the coil. It means that we are depleting all the energy stored in the AC tank. Sometimes all the energy amount stored in the AC tank is bigger than the energy transferred to the RL. So it means that we are losing energy a lot. So it is typically hidden energy caused for this type of energy transfer, but this is a huge loss energy so that it can be translated to the heat generation. Then here, how can I solve that issue? I wanted to let you know the 2 techniques. I want to skip one, but probably this one will be enough. So this method called cyclic on-off keying. In that case, here, this is an RC resonance, sorry. But we short the coil, again, at a very specific timing. When the voltage across the coil is 0, and the current through the inductor is at its maximum, we start the shorting. Then if we short the coil like that, then this maximum current flow through the inductor and the switch like a kind of DC current. Yes, there will be exponential decay, but still is a DC current. And then we completed the shorting after one single cycle. Yes, it is is equivalent to the suspended carrier modulation that we did in the forward direction. But even on the secondary side, you can do that. Then in that case, because of this single cycle, during the single cycle shorting, the current is completely changed, and then at the end and the beginning of the shooting, the phase in phase, so that when it resumes the oscillation, it can, this stored energy is directly used for the oscillation, so that it can recover to the original values and with the amplitude much more quickly compared to the previous case. Okay, let's compare this one with conventional LSK. So when Q2 equals 5, 10, and 20, and 40. Please note that here, when it resumes oscillation, because energy is stored in the acid tank, and then it resumes energy with the given stored energy, can recover to the original amplitude very quickly compared to the LSK. So LSK depleted all the energy by shorting, but in this case, it conserved energy so they can get much faster recovery, and also it stored energy by shorting there. So this is a resonant recovery time of the LSK, and this is a Cook cyclical on-off king. Even after the certain Q factor, even resonant recovery time gets smaller and smaller, so that you can achieve higher data rate. Yeah. Because this technique can be done at a resolution of the cycle, so that position-based data encoding can be done, so you can achieve the 2 bits per 4 cycles. So you can achieve 6.78 megabps at 13.56 megahertz. Also, it conserves more than 80% time for the power delivery. The power index is above the 80%. Here's some results. So when after the single cycle shorting, the acid tank immediately recovered to the original values. And then in the primary side, which is the receiver side, there is a voltage steps, so that we can detect the data by observing the voltage synchronously. And yes, this can be, so when there is a short on the first position, voltage step happens first. When there is a second shorting at the second, voltage step in the second, and so on. This is great. And so you could achieve 6 megabps, half frequency data rate at the 13.5 Mbps, but still there's some room to improve, which is this one. There's a shortings. So it means that 20% of the time we cannot transfer the power. So still, there's some method that tackle this issue. You need to understand that we need to understand this effect, the resonant frequency splitting effect. So here, when we decrease the coil distance from between the 2 coils, then what happened here is, this is a link gain. The red one is a 15 millimeter, blue one is a 10, and then black is a 5. The resonant peak is split when the 2 coils have very tight coupling. Yes, when it is a moderate or light coupling, yes, it has one single resonant frequency. Resonant frequency determined by the L1 and C1, and then L2 and C2 separately. But when there's a tightly coupling, then they affect each other, so that resonant frequency gets different shaded, so that it has 2 peaks. Like as we decrease the frequency distance, the resonant frequency is split that way. Then we can utilize this effect. Then here, in the transmitter side, we have an acid tank, and then we design a LC resonator, LC oscillator using this acid tank. Then resonant frequency or oscillation frequency will be determined by L1 and C1 in general. But because of the tight coupling, the resonant frequency is determined by the whole circuit, even including the implant.
Now L1 and C1, L2 and C2, they do resonate at two different frequencies, right?
Yep.
Okay,
No, and individually, I think you have them set to the same frequency, right?
Sorry,
Individually, if they weren't coupled, they're the same resonant frequency.
That's right.
You get the splitting because of the tight coupling. It's a fourth order system.
but why is it showing when the distance is so big?
It's not. If the distance gets really big, then they're loosely coupled, then you
Well,
eventually see one.
Probably.
The opposite.
The other way. Yeah,
Opposite.
I've seen it the other way.
yes,
That's why I was confused.
okay, good. Yes, when the distance is smaller, then there will be. So, so we have, now we have rather than having a just switch, we have another capacitor and then another one switch. So we switch the resonant frequency there. Then here we at certain frequency, we send out the data, power at this frequency. And then by changing the capacitor, we can switch to another frequency. Then it can get oscillated at another frequency. Then we can, by make a change in the secondary side, we can switch between the one frequency to the other. And then please note that on the receiver side, my power receiver side, the amplitude of the power signal is relatively constant, so that we can conserve the continuous power delivery. On the data receiver side, which is the power transmitter side, the frequency is changed, so that it is kind of frequency shift keying. So it's relatively easier to demodulate than the amplitude case. So they call the load-induced resonance shift keying, developed by your neighbor, UCLA. And then we utilized same thing for the other direction. Please note that this one, we are transmitting data from the implant to the primary side, but we can utilize the same effect for the other direction. Rather than having the LC resonant oscillator, we just drive it using the voltage controlled oscillator with the two different frequency. Then still we can transmit the power with a constant amplitude, and then we can continuously transmit the power. And then also the implant is a data receiver too. In that case, the data is a frequency modulated, so it's relatively easier to demodulate. Okay, this concludes my talk. So here, the frequency splitting FSK can be used for the forward telemetry. So in that case, we could achieve 2.5 mega BPS using these two carrier frequency. And then in that case, we increase the powering index to the 100%. And then this is the summary for the backward inductive telemetry. So LRSK can be achieved at 5 mega BPS with using the 30 megahertz, and then Cook could achieve the 6.78 mega BPS data rate. And then I contributed to this work before. And thank you very much.
It's a BPS thing. Is that the one that you skipped?
Oh yeah, I skipped it.
It seems like it's not as good though. I guess the data rate's 0.85.
That's right. This is called the passive phase shift keying. By shorting the coil, we could achieve the phase shift passively. Then they could achieve relatively high data rate, but still there's some drawbacks there. So yeah, I just skipped it for the time. Any further questions? Okay. I hope that talk you could understand some material from my talk. And
Could you share your slides with us?
Yes, I can.
I
Yes,
think that this is really useful, like for the students, like tutorial style, to, like learn about these methods. Be
yes,
able to go back and study them.
yes, I'm happy to.
It's also recorded and will be posted online.
You asked for permission for that,
Yeah, of
right?
course.
Okay.
Yes, yes.
So the cook is is that the leading technique right now?
In terms of a data rate,
Where are they?
but there is some limitations. So they cook, and also the frequency splitting FSK requires high K. So when there is a high K, then we can utilize frequency splitting FSK, and then or load induced.
So you need to have a broader resonance base, right? And you need to have the coupling so that it affects the oscillation frequency.
That's right. So it is for very certain applications. Yes.
So from this table, I realized that very important is like the favorable frequency for the network inductive thing. So in this case, is there any specific reason or choose this? Because this is I use.
Yeah, ISM band. So it is an approved band so that we can utilize it. But there are other ISM band depending on the country. But for example, 144 is another option too. 144 meg. Oh,
So that this is standard frequency.
yes, yes. Okay. Okay.
Okay, then thank you so much.
Thank
for your
you.
devoted time and a great presentation.
Thank you. Thank you for coming.